is computational fluid dynamics. I've been doing this for quite a long time, and I write CFD codes and I use CFD codes, and so we do work on numerical analysis and things, as well as on using existing codes. And one of the things that's really quite interesting at the moment is, and people have already touched on this, is this idea that you've got flow here from some kind of CFD model impacting on some kind of model of a tidal turbine, but you've got a rotor that's moving in response to that flow that goes all the way through a power system and into the network. And if you have an array of turbines, they are electrically connected and hydrodynamically connected, and that means that we really want to have a model inside the CFD code or in the lab, which is taking into account the fact that both the hydrodynamics and the electrical stuff is connected. So you need to be working with electrical engineers looking at what's going on at this end, with mechanical people that are telling you how this is going on, and then we need a CFD code that does the turbulence, boundary layer, and all sorts of other stuff to make sure that all of this goes together. And we can then put that into arrays of turbines in a simple channel in this case, and we can look at how long does it take the wake to mix out, what's going on in the flow physics between the wakes as they're mixing, and try and understand what's going on in that kind of thing. So from a CFD modelling point of view, this is the kind of thing where you can have lots of fun, and more importantly, you can burn thousands and thousands and thousands of hours on that supercomputer at the other end. I have a long-term interest in waves and splashing. A long time ago I did some work with Tom Bruce on coastal engineering. One of my PhD students got in terrible trouble because he went for a romantic weekend with his girlfriend to Whitby and spent all his time taking pictures like this of waves breaking. But we want to know why you see the structure that you see in a breaking wave, and we think we can understand that from a mathematical analysis. And the question now is, what can we do with that knowledge? We know why the waves break in a particular way. What does that mean for wave-induced vibrations on monopiles during storms in offshore wind farms? What does it mean for the interaction of floating devices with waves that are breaking in this way? So can we use this new knowledge to improve the design of machines? So romantic seaside weekends ruined by research is guaranteed. And the last thing is some work that we've been doing for a long time on floating offshore wind. This is a floating offshore wind platform that mounts two 5 megawatt wind turbines on a semi-sub being tested in flowwave. And the interesting thing about this is that the wind force pushes the semi-sub back, so it floats at an angle. It's not floating in the way that it was designed. And if you look at the effect of that angle on the response amplitude operators, you can see that at 10 degrees, positive 10 degrees heave, which is quite easily achievable, the behaviour of this platform is completely different from what the 0 degrees operation is, which the naval architect who designed the platform had in mind when they designed it. That affects the mooring dynamics, that affects the hydrodynamics. So if we want to test this properly in the lab, then we need to start using software in the loop controllers to simulate things that we can't model in the experiments. And we possibly need to optimise things like that, and possibly even we need to start hybridising numerical CFD models with experimental work and have hardware in the simulation and simulation in the hardware.
Okay.
And that's it. Good, thank you.
This production is brought to you by the University of Edinburgh.